welcome to another Aldic Riviera-PRO video. My name is Chantel, and I'll be going over the variety of tools available within Riviera-PRO that are useful for debugging UVM transactions. While a UVM scoreboard already has the responsibility of checking for correctness of the output data, it may be important to also analyze the transactions to get a better insight on what's happening to the design during the test. So, to get started, I have this UBus example design opened up. This can be found by going to Riviera-PRO's Examples folder, then expand System Verilog, expand the UVM 2020 folder, expand Integrated, and then there's the UBus design. Now, in this example design, I'll be running simulation with the runme_tr macro. This macro will turn on signal linking with the transactions for UBus bus monitor and the slave sequencer stream, which we'll be able to see later in the Waveform Viewer during simulation. This macro also has the Aldic Recorder class set as default and activates the transaction stream viewer and the Waveform Viewer after running all of the simulation. So now I'll go ahead and execute the macro. With the simulation now finished, we can see a complete view of the transactions that had occurred during simulation, both in the transaction stream window and the Waveform Viewer. I'll first talk about the Waveform Viewer. Thanks to the commands in the macro, all of the transaction streams have been added to this window. Currently, the name of the transaction stream and the names of the transaction data inside of the stream, the hierarchy of the transaction stream, and the values of the transaction data are all displayed. Setting my cursor along different simulation times updates the values and names displayed in the information columns. Each of the green outline boxes inside the waveform are transactions. It shows when this transaction began and when it ended. When clicking on the little plus button, the transaction box expands and more information is displayed. This updates the name and the value column. For example, in this slave memory sequencer, a request transaction is made at 130 picoseconds. By expanding the box and clicking within the time frame that the transaction was active, I can get information about this transaction, such as the data, wait state, and address. The transaction stream viewer also displays the name and hierarchy of the stream. If not already added by a macro, right-clicking on the selected streams opens up the context menu and allows for adding the stream to the waveform. You can also expand the transaction and view the signals associated with it. Being able to visually see the timing of all the transactions can help with confirming whether or not the UVM test bench and the design are working as intended. Now, once the UVM end of elaboration phase during simulation finishes, the UVM graph becomes available. Go over to View, UVM, and then UVM Graph, or just click on this icon over here. And then the graph of the UVM model appears. Here, you can view the test bench architecture and its data flow. The rectangles are all UVM components, and the arrows show the TLM connections and their directionality. The little icons denote the type of UVM component. For example, all the slaves have the agent icon next to them, and we can see how each slave has a monitor, sequencer, and driver with their connectivities shown. So, along with being able to see the timing of the transactions, we can also graphically check to see if the TLM connections are connected as expected. If they're not, then it could be the reason that one or multiple transactions may not have worked as expected. There's also the UVM Hierarchy window. You can access this by clicking on this icon, or by going to View, UVM, and then UVM Hierarchy. This shows a hierarchical tree of the UVM components and their parent-child dependencies between them. If you're stepping through simulation, you can toggle tracking of the currently selected UVM component. Again, like in the UVM Graph, you can see the slaves have a sequencer, monitor, and driver. When highlighting any of the UVM components in the hierarchy pane, the Properties pane of the hierarchy window also updates. Here in the Properties pane, you can see the type of component as well as its value. This pane also allows you to expand the object and view the subcomponents associated with it. Back in the hierarchy pane, if you right-click on a selected UVM component, you can show where the component is on the UVM graph using Show in UVM Graph. The other way works too. When clicking on a component in the graph, that component gets highlighted in the hierarchy window. Now, there's another window that can be accessed for UVM testing. It's called UVM Configuration. To access this, just click on this icon, or go to the UVM option in the View tab of the bar. This presents the available resources in the UVM database during simulation. This is where you can see the values of these configurations, as well as their properties, similar to the hierarchy window. I'll now end the simulation and close some of the windows. And I'm going to open up one of the files called ubus master driver. And I'm going to set a breakpoint in this line for drive database, which is part of the drive transfer task of this ubus master driver class. Then I'll open up call stack by clicking on this button here. This will show the HDL subprograms called during simulation. In this case, for the UVM test bench, it should show system verilog functions and tasks. Now I'll highlight these two lines in the transaction macro and click on Execute Selection. And see how the simulation has paused because of the breakpoint I have set earlier. Now the call stack window has some subprograms in it too. The most recently called subprogram is the one at the top, with the calling subprograms that led to it being below it. This window only shows the processes called by the currently executing processes. The yellow arrow and highlight indicate the statement executed in the innermost subprogram. And double-clicking on the other subprograms highlights it with a green arrow and highlights it in green in the HDL editor. This can be useful for debugging transactions if a certain task, function, or process wasn't called when it was supposed to. One last window I'd like to show that may be useful for UVM transaction debugging is the cover group window. This displays the cover groups declared in the design. Here we can see the name of the cover group and the cover group's instances and components, the number of hits for the cover group or its components, the type of coverage object, and the object's hierarchy. As I continue to run through simulation, the number of hits in the cover groups listed also updates. By expanding these cover groups, we can see that these cover parts of a transaction, such as the address and the data. You can also right-click on a cover group object and show its source in the HDL code. Being able to see these and the number of hits in these cover groups can help with determining how well the transactions cover the different possible outputs of the collected data from the transactions. And that essentially covers the many tools that you can use for UVM transaction debugging. Many of these can also be useful for overall UVM design, as well as general debugging. Utilizing these tools will bring a lot of insight into your UVM transactions and overall test bench design, making debugging and analyzing your transactions easier on you. Thank you for watching.